All right. What do you guys know about kyanite? I think we've talked about it before. I don't think we've done a mineral segment on it, however. I don't think we've done a mineral segment on it. You just got some kyanite last week? What's your favorite thing about it, Science Streams? I'm going to go over everything. It is blue. Mostly. Usually it is blue. Do you guys know anything about the hardness? There's something about this particular mineral that's different with its hardnesses. It is brittle. It's actually not super soft. It has nothing to do with how hard or soft it is. It actually doesn't have to do with the number. There's something different about this particular mineral's hardnesses. It does depend on the axis. That's exactly right. There are two different hardnesses. That's what I'm getting at. There are two different hardnesses in kyanite, which I think is pretty damn cool. There. The samples that I have are from Brazil. I make these individually per mineral. Did you guys know that? You know that now. It is an aluminum silicate. Yes, that is correct. It's aluminum silicate. That is correct. So kyanite, I don't have any varieties that look like this, and I've never even seen any in person that look green or red. This is very, 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 very distinct of kyanite. This is a really nice sample. It's exceptionally well-developed, gemmy. But typically, kyanite really doesn't. Typically, kyanite looks like this. Like this. Just big blue, bladed, long shards. They're very, very flat, they're thin, and they're very long. They're very, very resistant to pressure. And it's because they're a metamorphic index mineral that form under high pressure conditions specifically. So, I've got a couple of pieces of kyanite that I can show you on my camera here. So this is what I mean by bladed. They're very flat, right? Oops. All right. Do you see how flat they are? If I were to turn all of these on their side, it would literally be that thick. They're very, very flat. So they're very, very flat and thin and bladed. And this is where it gets really weird. Their hardness is completely different. So this would be the C-axis. There's 3 dimensions when you talk about the crystallography of a mineral, A, B, and C. And the C-axis is oftentimes what things are referred to, I suppose, in reference to the C-axis. So the C-axis is parallel to the long. Here's the cool thing though. The hardness going this direction parallel to the C-axis is only a 4.5, where the hardness going perpendicular roughly to the C-axis is actually about a 7. So going this way, 4.5. This way, about a 7. So it's very, very unique. And one of the reasons gemologists don't want to deal with this for jewelry is because of the differences in hardness. This is a gemmy variety of kyanite that I've actually never looked at under the microscope camera, and now we get to. You can tell how much darker it is. It's just so much nicer. And these are a bunch of other samples of kyanite that I have. This is something I'm not sure. I need to figure what this is. I don't think it's kyanite though. It could be stibnite. I don't think it's stibnite. I don't know. Anyway, I need to figure that one out. But these are very, very common in just rocky masses. In fact, you can see a lot of the ground mass still in there from whatever rock this was found in. And again, this is a really good index mineral for metamorphics because it specifically occurs in high pressure environments, very, very high pressure environment. It has perfect cleavage and imperfect cleavage at 79 degrees. So they intersect at about 79 degrees. And again, the hardness is different on 2 different planes. Some literature says 6.5, some says 7, going perpendicular to the C-axis. It's usually blue, but it can vary considerably depending. It's vitreous to pearly in luster. I would say that these samples here are pearly, whereas these ones would be much more vitreous. They're much shinier, so to speak. It comes from the triclinic crystal system, so that's of the 6 crystal classes, that is the one that it forms in. it's got a decent specific gravity. It's a bit dense of 3.67. It's transparent to translucent. It'll never be opaque. It's not going to have any kind of metallic luster like sphalerite does. Sphalerite is a bit unusual and interesting in this way. It's very fibrous, columnar, and bladed. Those are the ways that this mineral typically forms. And when it fractures or cleaves, the fractured and cleaved planes typically produce little splinter. It's kind of a splintery type breaking of the mineral. And cleavage, again, if you don't know what it is the breaking of the mineral on the atomic plane due to or based on the atomic structure of that mineral. Oh, it's a nesosilicate. Of the silicates, it's a big, big group of minerals, and there are many different types of silicates that form, and this is just one of them. And all it has to do is with the structure specifically. How the SiO4 tetrahedra work in each of the silicates can be very, very different per group. It does occur in igneous and metamorphic rocks, and potentially you could have it in a sedimentary basin, but they are not going to withstand weathering very well. And by they, I mean it's two other polymorphs, kyanite or sillimanite and andalusite. So the formula there, Al2SiO5, is for kyanite, but it's also the same chemical formula for sillimanite and andalusite. And in fact, these all three minerals occur in specifically, typically metamorphic environments. They're very, very, very useful too. The difference between the three is literally how the atoms are arranged between one another. And it all has to do with differences in temperature and pressure. So this guy here. So you'll see that on the X and Y axis that pressure and temperature increase. Right? Temperature on the X axis, pressure on the Y axis. And basically there are many, many models for this. They all differ slightly based on the author and based on their own data that they have, but they're for the most part pretty similar and the same. And you've got sillimanite in high temperature conditions. Well, I guess it would be high temperature and pressure in some cases. Andalusite is basically low pressure, and kyanite is high pressure. Kyanite is basically always referred to as the high pressure of the three. Andalusite, or no, I think it's sillimanite. Sillimanite is the one. Yeah, sillimanite is the one of the three that's difficult to mine because it's so fine grained. So it typically doesn't get used industrially like andalusite and kyanite do. And they are very, very, very widely used industrially as well. So again, these are the same formulas. It's just, you'll notice that there's a 4, and the aluminums are different. There's 6 alumina. That literally has to just do with the structure. That's it. It has to do with the arrangement of those things, not the quantity of the aluminum, but the actual structure itself. You'll notice that they are superscript letters, not subscript. If they were subscript, that would indicate the quantity. Make sense? I don't have any andalusite or sillimanite, but I'm going to show you guys pictures. So here is some andalusite. So we've got some nice prismatic crystals here. It's actually not a super, super pretty mineral. Mindat makes it look real nice though. Sillimanite, Mindat. Starlight's the one I want a sample of. Here is sillimanite. Andalusia. Oh, that's cool. I didn't know that, Bokimoto. Andalusite is first discovered in southern Spain. I don't know. They're usually, when you look, let's look at andalusite first. Andalusite was first analyzed by Werner on specimens coming from Spain. You actually might be right. Andalusia. They believe the specimens came from Andalusia, which was why the latter named it andalusite. They actually didn't come from, they came from Guadalajara. But it was a town they erroneously thought to be Andalusia. Its hardness is slightly different too because of the structural differences. 6.5 to 7, 6.5 to 7 versus 4.5 to 7. So they're not exceptionally pretty minerals. This is probably the prettiest thing you're ever going to find of silimonite. I wouldn't mind a sample just to be like, hey, these are the 3 polymorphs. Look how different they look. Yeah, they all have aluminum. They all 3 have aluminum. Andalusite, silimonite, and kyanite. All 3 of these are the same chemical formula. They have just different structures because kyanite forms in low temperature, very high pressure conditions. Andalusite in kind of moderate temperature, low pressure conditions. Silimonite in high temperature, and all pressure conditions. All right. Okay, back to kyanite over here. Let's see, it's triclinic. It can contain minor amounts of iron, titanium, and chromium in its crystal lattice and trace amounts. Twinning isn't obvious in hand sample, but it can happen. It's just not exceptionally common like it is in things like starlight, for example, which looks like this. So you can see all these different crystals growing out. This is very, very, very common. These are twins. I've always wanted more of the metamorphic index minerals. That's a nice sample. They're usually really not all that like spectacular, but the shape is what makes them exceptional. And the shape, especially if you're out doing field work and you come upon this mineral, then you know some metamorphism has happened somewhere. That or it's just been somebody. And if there's been no metamorphism, then somebody put that fucking rock. Maybe. All right, this is another metamorphic index. Do you guys know what that means? Metamorphic index mineral? When I say that? All right. That means that in metamorphism, so it's a group of rocks, right? And these are minerals. But in this particular group of rocks, different conditions can make different types of metamorphism happen. You can have contact metamorphism. You can have regional metamorphism. You can have all sorts of different types that are high pressure, low temperature, high temperature, low pressure, just all sorts of different environments that different things can form. I mean, we've got this chart for these 3 minerals, right? So let's say you're hiking around and you're looking for, you're mapping some metamorphics and you're trying to go from low to high grade. Well, low grade means it hasn't been metamorphosed much. Maybe it's just been low temperature, low pressure, a little bit, because there is a gradation to this, and you can have retrograde, so that means you can go backwards in some cases too. So back to what are index metamorphic minerals. If you don't know me, I'm a geologist. I teach on Twitch, and I also play video games, and I scream at everything in an insane way. Right, back to the science. All right. So metamorphic. So again, there can be a high to low grade. So you've got rocks that have undergone various temperatures and pressure conditions. Well, minerals, not rocks, because minerals make up rocks, but various minerals can appear in these rocks pretty distinctly. And by seeing those minerals in these rocks, you'd be like, oh, kyanite is in this particular metamorphic rock. Therefore, that rock had to have formed under these pressure conditions here. Okay, let's say you found some silimonite. Well, then you know it's not under really high pressure conditions, right? Or andalusite, for example, or starlite, or garnet. There are a lot. And different types of garnets too, mind you. There's a lot. All right. Now do you understand what a metamorphic index mineral means? It can be used in jewelry, and can be indicative of copper ores as well. Again, it is an index mineral for metamorphics, and it can occur in igneous and other rocks, but again, its weatherability is really poor, so it's not going to withstand sedimentary environments, which is why I've personally never seen it, or its other polymorphs, andalusite and kyanite, or silimonite. There's one perfect cleavage plane and one good cleavage. Do you guys have questions so far? This is one of the confusing things. Feel free to ask questions while I continue to talk too. This is one of the things about kyanite specifically that drives me nuts, is that its fracture and its cleavage can both be considered splintery. But the cleavage planes are pretty damn distinct. So at least the perfect one, as you can see it, it's the bladed flat side. The tenacity of this mineral is brittle. So again, with whatever stress you put on it, it's not going to deform elastically or plastically. It's actually going to snap brittly, like diamonds or many other silicates. Its streak is white, so if I were to take it on the streak plate, like I have, you're not going to see it on the white one, so we're going to use this one. This was from sphalerite earlier. But yay! It's got a white streak. It's perpendicular to the sphalerite one. It's the one closest to my hands right here. I'll do it again if you don't believe me. I'll do it parallel to the sphalerite streak. There you go. It's white. Actually, you can see how this is slightly off white now relative to the white streak of the kyanite. This particular mineral is colorless in thin sections, so if you were to look at it in plain polarized light, it would not display anything. It would just look clear. It can be gray, white, and light green. So we saw that on Mindat, that it was light green, which is crazy. I've never seen a sample of kyanite look like that, but it's really, really pretty. It's probably exceptionally expensive, too. All right, it can alter to cerussite, which is basically a phyllosilicate. So it's a mica, essentially. And we'll go over that in a minute, but not in detail because the next one is going to be muscovite, not cerussite. It can also alter to chlorite, which is another phyllosilicate. And it's a big, big group of silicate minerals that include a lot of micas that you probably are familiar with, like biotite and muscovite. Those are the two big ones that most people know about. They're white and almost black. It's it's very, very dark, almost black with a kind of a goldish sheen to it. It's kind of strange. The composition of the metamorphic rocks from which kyanite specifically comes from are a lot of mudstones and shales. That's the parent rock that's often metamorphosed before you get kyanite. And it's typically because there's a lot of aluminum content in mudstones and shales. So you have aluminum, you can get aluminum silicates. Andalusite's the low temperature pressure. Yeah, we've talked about that. It's typically found in contact metamorphic areals, shallow intermediate depth, intrusives, and low pressure rocks. Sillimanite is found in rocks subjected to higher temperatures. Kyanite, of course, is high pressure metamorphism. And here's an interesting tidbit. Kyanite can actually be found in granitic pegmatites, but the why is kind of unclear. There's still a lot of suggestions as to why that's happened, and I don't know. I don't know why it's found in granitic pegmatites at all. And again, all three polymorphs are unstable at superficial conditions, so they're going to weather out of the system very, very quickly. When it comes to weathering and erosion of any kind of rock and deposition into a basin. And then finally, the uses of kyanite include quite a bit, especially for heat resistance and pressure resistance. So heating aluminum silicates can actually produce a molite and then also quartz. So it produces two different things. It produces quartz and molite. Molite is actually used industrially, and it's structurally similar to sillimanite. But like I mentioned earlier, sillimanite is too fine-grained to mine. So they instead mine kyanite and andalusite and heat it to produce molite, and then they use molite to make high alumina bricks, line blast furnaces, ladles, kilns. It's all sorts of things to basically for high T and high P resistance. Oh, the name kyanite comes from the Greek word kynos for dark blue. And gem quality specimens are found in Brazil, Switzerland, and North Carolina. It's also used in spark plugs, heat resistance porcelains. Again, a lot of heat and pressure resistant things. In fact, I don't know if this is true, but I heard something about EJSA saying, I don't remember if it was EJ. I think it was EJ saying something about kyanites and basically aluminosilicates being used for rockets. The refractive index is between, it's basically 1.7. It is 1.7. It's 1.71 to 1.73. Yeah, kyanite has an insane amount of uses, which is why I voted on it. I mean, muscovite does too. I'll explain that. There's a lot of uses for muscovite as well, but I personally just like kyanite the best. Let's look at kyanite under the microscopes. This is the fun part. So there's the pieces of kyanite that I showed you that have ground mass in them still. This one, however, is just kyanite. It's got a gem quality one and a regular quality one. All right. Here is the one of the cleavage planes of kyanite. Doesn't look super fantastic. It just looks basically the same as in hand sample, right? It's not too crazily different. This is one of the other ones that's thicker. It's a little bit thicker. Technically, yeah, that is true. If I chuck a crystal at her, I am technically charging it with kinetic energy. That's very good. You're very smart. You're learning the things. I approve. So this is the thin side. This is the flat side of this bladed mineral. I really want to look at this. This is the gem quality one that I was gifted. I wonder what was going to be done with it, if anything. Because he does, that individual that gave it to me makes jewelry. There's some nice surfaces on here. There's also some other... Ooh. Some translucent planes right there. God, I really like this. Come on now. Okay. Ooh. This one isn't as exciting. Honestly, I think this one looks nicer just with your eyes. It just looks nice with your eyeballs. Like I just don't think it looks that much better with a microscope. Ooh, interesting. Something is in there. You could see through it. That's pretty cool. It does have a lot of cracks, yeah. Like this one does too. This one is exceptionally vitreous. And it's got a nice blue color to it I like.